Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to just take a second and look around you. Think about the device you're listening on, the coins in your pocket, maybe the ring on your finger. Every single atom of the heavy elements in those things, copper, nickel, gold, silver, anything heavier than iron, really, is an ancient relic.
It is. It was forged inside a star, or maybe a dying star, or in some cases, a star that exploded in just a cataclysmic event.
We're literally made of stardust, and we're standing on stardust.
That's not just poetry. It's literal truth. And for physicists, figuring out the exact recipes for that stardust, the cosmic mechanisms that build everything from the ground beneath our feet to the phone in our hands, that's one of the big fundamental quests.
And for a long, long time, it felt like we had most of that recipe book figured out. We had our two main characters, right? The two protagonists of element creation.
Right. The S process and the R process, the slow and the rapid.
Exactly. We thought we understood the slow, steady way elements were built, and we also thought we understood the violent, explosive way.
And they did a remarkable job. I mean, they accounted for a stunning amount of what we see out there. If you looked at the chemical inventory of our own solar system, those two processes gave you this beautiful, almost textbook explanation for how you get from iron all the way up to uranium.
But that's where things get interesting, because modern science, specifically modern astronomy, got a lot more precise.
It really did.
And these new, incredibly detailed observations of certain types of stars started sending back data that, it just didn't add up.
The numbers were just wrong.
Yeah, the ratios of elements they were seeing, things like strontium, deuterium, zirconium, they just couldn't be explained by the slow process or the rapid process. It was like finding a dish that had ingredients from two completely different recipes that shouldn't work together.
It was a huge signal, a persistent anomaly that told us our cosmic recipe book was, incomplete. Astronomers were seeing the final products of a process that had to be, something in the middle. Not slow, not rapid, but some kind of middle ground our models just weren't ready for.
And that's exactly what we're going to be diving into today. We are unpacking the proposed solution to this cosmic puzzle, the intermediate, or as it's known, the I process. We're going to get into the physics that makes it so unique, explore the really mind-bending experimental challenges of trying to measure it here on Earth, and, this is the amazing part, talk about why solving this mystery have these surprising, profound implications for technology we use every day.
It really does. I mean, we are talking about designing the next generation of nuclear reactors, for one.
It's incredible.
This whole field requires this amazing convergence of expertise. You've got the biggest telescopes in the world, the fastest supercomputers running simulations, and the most powerful particle accelerators, all working on this one question. Where did all the elements heavier than iron really come from? It's still one of the biggest unanswered questions in physics, and this I process might just be the key to unlocking the final chapters.
Okay, so before we get to the I process, let's just lay the groundwork. Let's talk about the core mechanism, because when we say creating elements heavier than iron, we're almost always talking about one thing: neutron capture.
Yes, that is the engine, absolutely. For everything lighter than iron, carbon, oxygen, the stuff of life, that's all built through stellar fusion, just burning hydrogen into helium, helium into carbon, and so on.
That's like a furnace.
It's a furnace, exactly. But once you get to iron, that furnace shuts down. Iron is the ultimate ash. Fusing iron actually costs you energy instead of releasing it so the star hits a wall. To get any heavier, you have to switch to a completely different mechanism.
And that mechanism, for over 99% of the heavy elements, is neutron capture. Could you just walk us through the basic physics of that? How does it work?
Of course. So you start with what we call a seed nucleus. Think of it as an iron nucleus, which is very stable. This seed is sitting deep inside a star in an environment where there's a flow of free neutrons floating around. The iron nucleus will, every so often, grab one of those neutrons. It captures it. Now it's a little heavier. Maybe a bit later it grabs another one. So its mass is going up step by step.
But it's still iron, right? Because the number of protons hasn't changed.
That is the absolute key. It's just a heavier isotope of iron. But if you keep packing more and more neutrons into that nucleus, Eventually, you reach a tipping point where it becomes unstable. It's radioactive. It has too much tension.
And it needs to relieve that tension somehow.
Exactly. And it does that through a process called beta decay.
And this is where the magic happens, so
Yeah.
to speak. This is the transmutation. What happens in beta decay?
So in beta decay, one of those extra neutrons inside the nucleus spontaneously transforms. It turns into a proton, and it spits out an electron to keep the charge balanced.
So you've just added a proton.
You've added a proton. And when you change the number of protons, you change the fundamental identity of the element. You've climbed one rung up the periodic table. Iron becomes cobalt. Cobalt becomes nickel, and so on. It's this beautiful step-by-step ladder, all powered by this cycle of capturing neutrons and then undergoing radioactive decay.
And you mentioned earlier that the speed of this process is what really matters. That's what separates the two classical ways of doing this.
Precisely. It all comes down to the neutron density and the time scale. They dictate which path you take up that ladder.
So let's talk about the first path, the slow one, the S process.
Right, the S process, or slow neutron capture. This is happening inside certain types of evolved stars, specifically in what we call asymptotic giant branch stars, AGB stars.
So what are the conditions like in there? When we say slow, what does that actually mean in cosmic terms?
We're talking about a process that unfolds over thousands of years. It's a very leisurely pace. The environment has a neutron density that's, well, it sounds high to us, but it's relatively low for a star. We're talking maybe tens of millions up to a few hundred billion neutrons per cubic centimeter.
Which, on a nuclear timescale, is an eternity. It means the nucleus has plenty of time between one neutron capture and the next.
That's the crucial part. Because the captures are so infrequent, if a nucleus becomes unstable, it has all the time in the world to undergo that beta decay and stabilize itself before the next neutron comes along.
So it's always staying close to the most stable configurations.
Exactly. It walks a very predictable path right along what we call the valley of stability on the chart of all nuclei. And this clean, steady process is responsible for creating a lot of the stable, heavy elements we know, all the way up to bismuth, which is element 83.
But bismuth isn't the end of the line. If we want the really good stuff, the gold, the platinum, not to mention radioactive elements like uranium, the S process just can't get us there. For that, you need violence.
You need the R process, the rapid neutron capture process. This is the complete opposite extreme. It requires environments with apocalyptic neutron densities.
We're talking about a huge jump here.
A mind-boggling jump. For the S process, we were talking about billions of neutrons per cubic centimeter. For the R process, we're talking about densities well over 10 to the power of 21. A trillion neutrons per cubic centimeter.
That is just an impossible number to comprehend. What kind of cosmic event could possibly create that level of neutron saturation?
Only the most catastrophic events we know of. The leading candidates for a long time were the core collapse supernovae of massive stars. But more recently, the evidence is pointing very strongly toward the merger of two neutron stars.
When two of the densest objects in the universe collide.
Exactly. In that kind of environment, the neutron capture is so unbelievably fast that the nucleus has absolutely no time to decay and stabilize.
It can't keep up.
Not even close. The whole thing happens in less than a second. A nucleus just gets flooded, swallowing dozens of neutrons one after another, pushing it way, way out into the most exotic, unstable, neutron-rich territory on the nuclear chart. These are isotopes that might only exist for milliseconds.
And then what?
And then, after the explosion is over and the neutron flood subsides, this whole chain of incredibly unstable nuclei starts to decay back towards stability. It's this rapid accumulation followed by a cascade of decays that forges the heaviest possible elements, including the actinides like uranium and plutonium.
So for a very long time, that was the complete story. You had the slow, steady S process giving us elements up to bismuth, and the fast, violent R process giving us the really heavy, rare stuff. It seemed to cover all the bases.
It did. It was a really elegant picture. But then, as astronomers started using these new high-resolution spectrographs on very old, very pristine stars, they started seeing cracks in that picture.
The anomalies.
The anomalies. They were finding elemental signatures, these abundance patterns that were clearly made by neutron capture, but the ratios were all wrong. They didn't fit the slow path, and they didn't fit the rapid path. It was too fast for one, but not extreme enough for the other. It was a clear sign that there had to be a third way, a mechanism that fell squarely in the middle.
Which is the perfect setup for
Wow.
what was really a rediscovery of this missing link. The I process.
Yes, and structurally, it's very simple to define. The I stands for intermediate, and it sits, right in between the S and R processes, both in terms of how many neutrons are available and how fast it all happens.
So we're talking about neutron densities that are way higher than what you'd find in a typical one of those AGB stars.
Right.
High enough that the captures happen pretty quickly.
Yeah.
But still, many, many orders of magnitude less than the insane conditions of a neutron star merger.
Exactly. The density is sort of in this sweet spot, roughly 10 to the power of 14, maybe up to 10 to the 16 neutrons per cubic centimeter.
Okay, so what does that density mean for the timing?
It means it's fast enough to build up some really neutron-rich nuclei, pushing the reaction path a good way off that valley of stability we talked about. But it's slow enough that the whole process takes, say, hours, or maybe even a few days, instead of being over in a single second.
Now, the history of this idea is fascinating to me. This isn't some brand new concept that someone dreamed up last year. The idea was first proposed, back in 1977?
That's right. It was a compelling theoretical idea even then. But the problem was there was no solid observational evidence to back it up. So it was almost forgotten about. It remained this niche theory because we just didn't have the tools to go out and find its signature in the cosmos.
You couldn't drive the research because there was nothing to measure.
Precisely. You can have a great theory, but if you can't test it, it's hard for it to gain traction in the wider community.
So what changed? What brought the I process back from the dead in the last, say, 10 or 15 years?
In a word, technology. Specifically, huge advancements in our telescopes and our detectors. We're talking about new generations of both space-based observatories like Hubble and massive ground-based telescopes that can now analyze starlight with a level of precision that was unimaginable in the 70s.
And the key technique here is absorption spectroscopy, right?
Yes, that's the one. You look at the rainbow of light coming from a star and you see these dark lines, like a barcode. Each dark line corresponds to a specific element in the star's atmosphere, absorbing that particular color of light.
And the darker the line, the more of that element there is.
Exactly. And with these new instruments, we can measure that barcode with incredible detail, and that's when we started finding these really hard anomalies in very specific types of stars that were perfect laboratories for this kind of thing.
The research you're referencing specifically calls out carbon-enhanced metal-poor stars. Now, that's a mouthful. Can you break that down for us? Why is that type of star so important?
Okay, so that name is basically a description of a cosmic fossil. Metal poor is astronomer speak for a very, very old star.
Right, because in astronomy, metal is anything heavier than hydrogen and helium.
Exactly. So a metal-poor star is one that formed early in the universe's history, when it was still mostly just hydrogen and helium. It's a pristine sample. It hasn't been, polluted by generations of other stars exploding and seeding the galaxy with heavy elements.
So its chemical makeup is a much cleaner record of whatever nucleosynthesis happened inside of it, or to it.
Correct. And the carbon-enhanced part is the other key. It means that at some point, these old stars got a big dump of carbon onto their surfaces, most likely from a companion star that evolved and puffed away its outer layers. And when astronomers pointed their new, powerful spectrographs at these specific old, pristine stars,
they found the smoking gun.
They found the smoking gun. The ratios of certain heavy elements, barium, lanthanum, europium, they just could not be made by any combination of the S and R processes. It was the definitive evidence that a third mechanism, an intermediate one, had to be at work in these environments.
So let's talk about the physics of why. How does that intermediate timing hours or days create a different set of elements than the other two?
This is where it gets really cool. It's all about hitting what we call branching points on the nuclear chart. These are specific unstable nuclei where there's a competition between capturing another neutron and undergoing beta decay.
A fork in the road.
A fork in the road, exactly. In the S process, it's so slow, you almost always take the decay path. The nucleus stabilizes before another neutron arrives.
And in the R process, it's so fast, you just blow right past the fork. You capture another 10 neutrons before decay is even an option.
Precisely. But the I process, because of its intermediate speed, it hits some of these forks where the half-life of the unstable nucleus is on the order of hours or days.
The same time scale as the process itself.
Yes. So the nucleus gets to that fork and it sits there. There's a real competition. Does it decay or does it capture another neutron? And that specific timing allows the reaction path to zigzag in a way that is totally unique. It can bypass some elements that the CES process makes a lot of and create other elements in ratios that neither of the other two can explain.
So it's this unique timing that produces that specific anomalous fingerprint that astronomers were seeing.
That's it. It's the convergence of the astronomical observations with the nuclear physics theory that told us, yes, the eye process isn't just a possibility, it's a necessity. It's a required piece of the cosmic puzzle.
Okay, so it seems like there's a strong consensus that the eye process is real and necessary. Which brings us to the next, much more complicated part. How do you actually solve it?
Right.
Let's talk about this research ecosystem because it's not one person in a lab. It sounds like a massive coordinated effort across completely different fields of science.
It's a fundamentally iterative process. It's complex, it's expensive, and it absolutely relies on constant, detailed communication between these different groups. I like to think of it as a three-legged stool. You have observation, theory, and experiment.
And if any one of those legs is weak, the whole thing falls over.
It does. It all starts with the observers, the astronomers. They're the ones at the telescopes pointing at these stars and collecting the light. They provide the ground truth.
They're providing the what and the where. They're saying, look at this carbon-enhanced metal-poor star. It has 100 times more europium relative to iron than our sun does. Explain that.
Exactly. They provide the target. They give us the final abundance pattern and say to the other groups, your models, your experiments, they must reproduce this specific fingerprint.
So once they have that target, the baton gets passed to the theoretical physicists and the modelers.
And in some ways, they have the hardest job. Their task is to build a virtual star inside a supercomputer. They have to model everything, the star's temperature, its pressure, convection, these things called thermal pulses in AGB stars, and simulate its evolution and its nucleosynthesis over millions or billions of years.
I can't even imagine the complexity of those simulations.
They are monstrously complicated. And to run, they rely on a huge library of pre-existing nuclear data. Things like reaction rates, decay half-lives for thousands of different isotopes.
But this is where the problem starts and where the feedback loop begins.
This is it. When they run these incredibly complex models, they'll find that the final outcome, the amount of barium or lanthanum produced, is extremely sensitive to a handful of specific nuclear reactions along the eye process path.
Okay.
And often, when they look up the data for those critical reactions in the nuclear databases, they find that the numbers have what we call large uncertainties. The value might be known, but only to within, say, a factor of 5 or 10.
So the model basically says, okay, the final abundance of barium should be X. But because we're not sure about this one key reaction, X could be anything between 10 and 1,000.
Precisely. And that kind of uncertainty is completely useless if you're trying to match the very precise data coming from the telescopes. It's at that point that the modelers pick up the phone, figuratively, and call the experimental nuclear physicists.
Like Mathis Wiedeking, the physicist whose work we're drawing on today.
People exactly like him. The modelers go to the experimentalists and they say, listen, our models are completely stuck. The outcome is dominated by the uncertainty in this one specific neutron capture reaction on this one specific unstable nucleus. We need you to go to your lab and measure it for us. We need better data.
So this massive cosmic question gets boiled down to a very specific, actionable challenge for a team at a particle accelerator here on Earth.
Yes. Their job is to design an experiment that can reduce that uncertainty, to shrink those error bars. And it's this constant back and forth. The experimentalists provide new, more precise data. The modelers plug it into their simulations. The simulations get better, which then often highlights another reaction that needs to be measured even more precisely. It's a collaborative dance that's pushing our knowledge forward one reaction at a time.
So let's zoom in on that experimental work, because this is where the difficulty just goes off the charts. What is that single most fundamental piece of data that the modelers are always asking for?
The absolute number one, most critical ingredient for any neutron capture model, whether it's S, R, or I, is something called the neutron capture cross-section.
Okay, that sounds pretty technical. Is there a more intuitive way to think about what a cross-section is?
Absolutely. The easiest way to think about it is as the size of the nucleus from the neutron's point of view. It's the probability that if you shoot a neutron at a nucleus, it will actually get captured, that it will stick.
Yeah. So a big cross-section means it's a big, easy target. A small cross-section means it's a tiny target that the neutron will probably just miss.
That's a perfect analogy. And if you don't know that cross-section, you have no idea how often the capture will happen. And if you don't know that, you can't predict how fast you climb the periodic table. Your whole model falls apart.
Okay, so we need to measure these cross-sections, but this is where the huge problem comes in, especially for the eye process.
This is the massive challenge. Measuring a cross-section is, I won't say easy, but it's relatively straightforward if you're working with a stable isotope. You can make a physical target out of the material, like a thin foil, stick it in a beam of neutrons, and just count how many captures happen. Direct measurement.
But the eye process, by its very nature, doesn't happen with stable stuff.
Not at all. Because of that intermediate speed and neutron density, its reaction path wanders far away from the valley of stability. The nuclei that are crucial for the eye process are almost all unstable.
And when you say unstable, what kind of timescales are we talking about?
We're talking about half-lives that range from maybe a few days down to fractions of a second.
Which means making a physical target out of them is completely impossible. You can't make a foil out of something that disappears a second after you create it.
You absolutely cannot. So direct measurement techniques are off the table. And this is what forces scientists into this incredibly clever and complex field of indirect techniques.
Okay, this is what I really want to understand. How on earth do you do this? How do you measure the probability of a neutron capture without ever actually, capturing a neutron on the nucleus you care about?
It's a beautiful piece of experimental physics. It's a kind of substitution. So first, you need a very advanced particle accelerator facility, a place that can produce beams of these rare, unstable isotopes.
We're talking about major international facilities.
Yeah. Places like the 88-inch cyclotron at Berkeley Lab, or the new facility for rare isotope beams, FRIB at Michigan State, or Argonne National Lab. These are massive, cutting-edge machines.
So step one is you use one of these machines to create a beam of the specific unstable nucleus the astrophysicists asked for. That alone sounds incredibly difficult.
It's a huge challenge. Once you have that beam, you can't hit it with neutrons. So instead, you hit it with a different particle that acts as a sort of surrogate, a stand-in for the neutron. A common method is to use something called a deuteron.
A deuteron is the nucleus of heavy hydrogen, right? One proton and one neutron stuck together.
Exactly. So you take your beam of unstable nuclei and you shoot it through a target made of deuterons. When one of your unstable nuclei hits a deuteron, the deuteron might break apart. The unstable nucleus grabs the neutron from the deuteron, and the proton goes flying off.
So you've successfully added a neutron, just not a free one?
Correct. We call it a DPRP reaction, for deuteron in, proton out. Now, this is not the same as a pure neutron capture, but, and here's the clever part, by surrounding the collision point with incredibly sensitive detectors, we can measure the properties of that outgoing proton with extreme precision. Its energy, the angle it flies off at.
You're reconstructing the crime scene, basically.
That's a great way to put it. We're looking at the debris field. By applying the laws of conservation, of energy and momentum, and some sophisticated nuclear theory, we can use the information from that proton to work backwards and infer the properties of the nucleus we created.
And from those properties, you can calculate what the cross-section for a direct neutron capture would have been.
That's the final step. It's a very complex chain of logic and measurement. You have to account for every single bit of energy in the reaction. You need gamma ray detectors, particle detectors, all working in concert. But at the end of this enormous experimental effort, you can provide the astrophysicists with the number they needed, the neutron capture cross-section for a nucleus that only exists for a fraction of a second. It's an incredible bridge between the lab and the stars.
Okay, we've been deep in the weeds of neutron densities and unstable nuclei and particle accelerators. Let's pull back up for a minute and connect this all back to life here on Earth. Because I think for a lot of people listening, it might be hard to see the connection. Why should we, as a society, care about the neutron capture cross-section of some obscure, short-lived isotope? What is the tangible so what?
And that connection is often the most surprising part of this whole story. The fundamental nuclear data that is being painstakingly gathered to answer a question about stellar chemistry has immediate, and I mean immediate, relevance to some of our most critical technological challenges right here.
It's a classic case of pure, curiosity-driven research leading to massive practical payoffs. So let's break them down. Application number one, nuclear energy.
Yes. The data from these indirect measurements, specifically getting more accurate cross-sections for these unstable isotopes, is absolutely crucial for designing the next generation of nuclear reactors.
Why is that precision so important for a reactor? I think most people imagine it's just about, keeping a chain reaction going safely.
For older reactor designs, that's more or less true. But for advanced reactors, what we call Generation 4V designs, things like fast reactors or molten salt reactors, the physics is much more complex. They operate with different neutron energies and different fuel cycles.
Okay.
And to model how these reactors will behave safely and efficiently over a lifespan of 60 or 80 years, engineers need incredibly precise data. They need to predict exactly how the fuel will change or burn up over time. And that involves a whole chain of neutron captures and decays, creating all sorts of exotic, unstable isotopes right there in the reactor core.
So the same physics happening in a star is happening on a small scale inside the reactor.
It is. And if the cross-sections for those isotopes are uncertain, the engineers' models are uncertain. They can't accurately predict things like neutron poisoning, which is where some of these newly created isotopes are really good at absorbing neutrons and can actually stall the reaction if you're not careful.
So better data from astrophysics leads directly to safer, more efficient reactor designs.
Directly. When an experimental physicist manages to reduce the uncertainty on a cross-section by a factor of 10 for an astrophysical model, that same factor of 10 improvement gets plugged into the nuclear engineering codes. It takes this research out of the cosmos and puts it right into our future energy grid.
That's a powerful connection. What about application number 2? You mentioned medicine.
This is another huge one. This fundamental research directly benefits the entire field of medical isotope production.
You're talking about the radioactive materials used in things like PET scans or cancer therapy.
Exactly. Many of the most promising new isotopes for, say, targeted alpha therapy for cancer are very unstable, short-lived nuclei. And before a pharmaceutical company or a research hospital invests billions of dollars to build the infrastructure to produce a new medical isotope, they have to know if it's even feasible.
They need to know if they can make enough of it to be useful.
Right. Can it be produced in sufficient quantities and with sufficient purity? Answering that question comes down to knowing the exact reaction cross-sections. The data from the I-process research helps them determine the most efficient way to make a new isotope, what target material to start with, what energy to use for your particle beam, what your expected yield will be. It's a very practical, multi-billion-dollar decision that rests on this very fundamental physics data.
And finally, application 3, which you said extends into engineering and even national security.
Yes. Again, it all comes back to reducing those nuclear data uncertainties. Better data helps in any complex engineering field where you have to deal with neutron interactions, designing power sources for deep space probes, for example. But it's also vital for national security.
How so?
For things like nuclear non-proliferation and treaty verification. To be able to detect and identify nuclear materials, or to verify that a country is adhering to an arms control treaty, you need the ability to model and predict nuclear signatures with very high confidence. The more accurate our fundamental database of nuclear cross-sections is, the better our predictive and our verification capabilities become on a global scale.
So the quest to understand a weird chemical signature in a star 1,000 light years away ends up making our power plants safer and our world more secure.
It's a perfect illustration of how you can never predict where fundamental research will lead. You chase the answer to a deep academic question about the universe, and you end up developing tools and data that have profound benefits for everyone.
So let's bring it back to the cosmos for the last part of our discussion. We've talked about what the I process is and why it's so hard to measure, but there's still a huge open question, right? We don't really know what its ultimate contribution is.
That's right. The big unanswered question is about the termination point. Where does the I process stop?
We know this process kind of fizzles out around bismuth, element 83. It just can't build anything heavier.
Correct. The nuclear physics just doesn't allow it to proceed further. So the big question is, does the I process also hit a wall there? Or can its unique pathway allow it to go beyond bismuth?
And why is that specific question so critical?
It's critical because of what lies beyond bismuth. The actinides, elements 89 through 103. Things like thorium, uranium, plutonium.
The heaviest naturally occurring elements.
Exactly. If the I process is confirmed to stop at or near bismuth, then it solidifies the idea that the R process, those incredibly violent neutron star mergers or supernovae, is the sole source for all the uranium and plutonium in the universe. It means you absolutely need one of those rare catastrophic events to forge them.
But there's a possibility that's not the case. Some of the models, based on the data we have so far, suggest the I process could actually push all the way into the actinides.
That's the tantalizing possibility. If that turns out to be true, it would fundamentally change our understanding of cosmic history. It would mean that the heaviest elements in the universe don't only come from the rarest, most violent explosions.
They could be made in, what, slightly less extreme environments?
Potentially. Maybe in certain types of supernovae that aren't quite energetic enough for a full R process, or maybe in the evolution of stars that are a bit more massive than the ones that host the size process. It would mean the cosmic pathways to creating uranium here on Earth might be more diverse than we currently think. It would give us a crucial new actor in the story of element formation.
This field is moving so fast, it's really only been a major active area of research for about a decade. So looking ahead, what does the next 5 to 10 years look like?
It's going to be a period of really intense data analysis and experiment preparation. Right now, as we speak, there are teams all over the world analyzing data from experiments that have already been run. There are literally, as Mathis Wiedeking puts it, tens of data sets in the pipeline.
So we're on the cusp of some major new results.
I think so. The goal for the next decade is really to nail down the I process, to put it on the same solid, confident footing that we have for this process.
And what does that mean in practice?
It means designing and running a new generation of experiments to bring those experimental uncertainties way, way down. To get the cross-sections so precise that the astrophysical models no longer have huge wiggle room. They will have to make a firm prediction. And at that point, we'll know. Either the I process, with these new, precise inputs, perfectly explains the anomalies we see in those old stars.
Or it doesn't.
Or it doesn't. And if it doesn't, that's just as exciting, because it means our understanding is still fundamentally wrong, and it forces the theorists to go back to the drawing board and come up with something entirely new. Either way, the science moves forward.
It's just such an incredible story. You start with the metals in your phone, and you trace their origin back through billions of years to the fiery heart of a star we'll never see. And the quest to understand that star ends up inside a particle accelerator here on Earth.
It really is a profound link. The question of how elements are formed has been central to physics for, almost a century now? And the solution isn't coming from one field. It requires this massive international effort linking our biggest telescopes, our most powerful supercomputers, and these incredible high-energy accelerators.
It just underscores that to answer the biggest questions about the universe, you need the most complex collaborative solutions right here at home. Every chemical element that makes up our world was determined by the simple act of a neutron being captured by a nucleus billions of years ago.
And we're finally getting the tools to read that history.
Which brings us to a final provocative thought for you to take away. Let's imagine that in the next few years, all this new, precise data comes in from the global accelerator experiments. And it confirms, yes, the I process is real. But it also proves definitively that it stops cold well before the actinides. Let's say it terminates at element 85 and can go no further.
Okay.
What does that constraint, that new wall in our knowledge, actually tell us?
If the I process truly cannot bridge that gap, it intensifies the necessity of violence in the cosmos.
What do you mean by that?
It tells us something fundamental about the sheer rarity, the extreme physics, the absolute violence required to forge the heaviest elements. It means that to get the uranium and thorium that are in the Earth's crust right now, the elements that help power plate tectonics and geothermal energy, you had to have had an event as catastrophic as 2 neutron stars colliding nearby in our galaxy's history. There was no easier intermediate way.
So it reminds us that every single element, whether it's in our jewelry or our technology, tells this incredibly complex, fiery, and as we've learned today, still very incomplete cosmic story. A story whose final chapters are still being written right now in labs around the world.